mu is less than, just may as well put n equals 0. Between 0 and 1, the optimal value will be n equals 1, n equals 2, n equals 3, and so on. So you'll get something similar to what's called the charging diagram of a quantum dot. This is just a single site, like some quantum system, and you're adding bosons. And for a finite range of chemical potentials, either you have 0 boson or 1 boson or 2 boson or 3 bosons and so on. Okay, so that's the state at W equals 0. Now you ask what happens when W is non-zero. Do these bosons move around? Well, of course they're going to move around because this is going to huff the bosons. But what kind of state do they form? So that turns out to be a bit tricky. But let's sit here somewhere, especially the boundaries. Let's sit over here, say at mu equals 1/2, and ask what happens. So at mu equals 1/2, for example. So at mu equals 1/2, what are the different states that you can think of? So you put mu, u is u over 2, sorry. So what are the different values? The ground state energy is n equals 1. So if the ground state is minus mu, and there's no u, which is minus u over 2, you could put, so that has n equals 1. You could have n equals 0, and that has energy E0, and that's just 0. And then you could have n equals 2 and 3 and 4, but the others will have much higher energy. And E sub 2 will be minus u over 2 times 2 plus u. Yeah, okay, which is also 0. So if I look at the energy level diagram, there is a state with one particle at the bottom, and there are two states which exactly at mu equals 1/2 have energy 0. So this is minus u over 2, and these are 0. And this is n equals 0 and n equals 2. Okay, the fact that they're exactly degenerate is a special feature of the fact that I was exactly in the halfway, but I could be actually even away from that. And this won't be very crucial to what I talk about. All right, so what you notice that if you're somewhere in the middle between the transitions of these different integers, then the system has a gap. The ground state is unique, and it takes a finite energy to create excitations. And what that tells you is that perturbation theory in W is well defined for a certain regime, and the gap is also stable. So if you draw a picture of this, here's our lattice. So you have one boson on each side in the ground state. And what does W do? Well, W just moves the boson from one side to the other. So for example, it can move this boson over there. And so you have a pay an energy cost at this site, which will be u over 2. You'll also pay an energy cost of this site, which will be u over 2. And the total energy cost is u, which is, again, seems natural because now you have two bosons on a site and they repel each other. Okay, but now if you do further perturbation theory, what you're going to notice is that this particle, there's already a particle here. So this is some particle that you created, and this is in fact a hole. Now this particle can hop over there with matrix element W. And when it does that, there's no energy cost in the second process. This thing can move freely. So this just starts to move. And similarly, this hole can also move freely. And the reason there's no energy cost is, of course, you already paid the repulsion cost here. And once you go there, it's the same energy. The on-site energies are the same. So you have to treat this with degenerate perturbation theory. And similarly, this. So what you see from, if you just do this perturbation theory a little more carefully, and that could be another homework problem, you'll find that the excited states, there are two excited states. They are better thought of in momentum space. There will be a particle-like excited state, will have some dispersion, will be something like U/2 is the energy cost. And now this hopping will allow that particle to move. But one thing you have to remember when you hop here is the famous Bose enhancement factor. So when in this side is going from one boson to two bosons, or vice versa, and this matrix element, has the property that B dagger of n is square root of n plus 1. So that's the famous factor over here. And for this particle, you're going to pick up that factor twice, once here and once there. And so the dispersion then will be minus 2w times the Bose enhancement factor, which will still be 2, times sum on the different directions of cosine of ki. And there'll be hole-like excitation, which will also cost energy U/2 minus 2w, but this factor won't be there because you're going from 0, 1 to 1, 0, and cosine ki. So if I draw the excitation spectrum in a band, let's try it over here. So this is some band K. There's a particle-like band, a hole-like band, and a particle-like band, which has a bigger bandwidth. Okay, at least near this point. And there's always, we're assuming W is very small, so you have a feature which is called the gap, the energy gap. So this system is very, very different from the superfluid system we talked about last time. It has a unique ground state, one particle per site, at least at W equals 0. And if you do perturbation theory in W, you'll find it still remains unique. And the excited states come in two types. There's a charge 1 excited state and a charge -1 excited state, corresponding to the particle in the hole. And they cost a finite energy to create, which is this energy of order U/2 minus something times W. But W is small, so there's a range of W where the gap persists. Okay, so what we found is a very different type of state here. The present, which has a very special feature that the density of bosons is quantized. It has to be exactly one boson per site, and it has a gap. And this is the phase that we call a mod insulator or an insulator. So what I found here is a mod insulator. And similarly here, this is another mod insulator. There's another mod insulator. And these are stable states, as you can show to any order in perturbation theory, that must exist over a finite range of chemical potentials, where the density is exactly an integer. Yes?
In the first lecture, you discussed the distinction between a regular insulator and a mod insulator.
Yes.
How does it manifest itself?
Yeah, okay, no, thank you for pointing that out. I'm guilty of an abuse of terminology, but I'm not alone in it. This is a trivial insulator. So to be consistent with my previous notation, let's call this a trivial insulator. Yes. People do call it a mod insulator, but Mott himself never talked about bosons. Let's just call it a trivial insulator. Thank you. I think we should reserve Mott for electrons because that's all he talked about. So it's a trivial insulator, but you will find papers that call it a mod insulator. So, okay, that's probably why I made that mistake. Well, we shouldn't. So we'll call it a trivial insulator, and there's a trivial insulator n equals 1, trivial insulator n equals 2, n equals 3. And in fact, you can also think of the vacuum, the empty state, as the trivial insulator, except this is an empty state, which has only particle-like excitations. It doesn't have any hole-like excitations. And that makes this trivial insulator kind of special and leads to some of the peculiar properties that we saw last time, which I'll come back to once I start talking about field theories. All right, so another thing you can see here is that this insulating behavior, this conclusion, it has to be this trivial insulator, does not hold at these special points. These are gapless points. Let's say at mu equals 1. At mu equals 1, you can check that the n equals 1 and the n equals 2 states are degenerate. So here you have, you have an energy gap to creating a particle and creating a hole. Let's ignore W, so it's just a flat energy as a function of K. And then what happens here is that the energy to add a particle goes to 0, or as respect to the n equals 2 state, the energy to remove a particle goes to 0. So that's a very special point where I cannot trust this perturbation theory. That's also true here at this point at mu equals 0. Okay, but so then, in fact, in some ways, a major part of the remainder of the course will be answering the question of what happens at these points. That's where you get many more interesting possibilities, which I won't go into today, but that's what we're going to talk about in the next few chapters. In particular, you can also now notice that you've got a gap state with no broken symmetry. That's what I mean by trivial. There's no broken symmetry. It has a full gap. But this only occurs at integer values of n. So you can now ask, are there gap states with no broken symmetry at other values of n? Are these such things possible? And the answer turns out to be that in one dimension, the answer is no. And that's the Lipschutz-Mattis theorem. But in 2 and a higher dimension, the answer is yes. You can get gap states with no broken symmetry at other values of n, in particular rational values of n. And those are related to states with topological order, and that we'll talk about in some detail. But that's not for today. But that's kind of where we are going. So, but let's just first understand this particular model, which is now extremely well understood, and see what are the things that happen in the space diagram. So we've learned 2 things. One is that at small w, there are these trivial insulators with integer filling. And at large w or small u out here, that's what we talked about last time, there's a superfluid. And you remember in the superfluid, I didn't tell you what the density was. The density could be anything. The density was continuously variable. So what we call that as saying is compressible. It's a compressible state. You can have any density you want at 0 temperature, and it's a superfluid. And it's gapless, and it has a broken symmetry. So these are all the features that we were underlying what we talked about last time. And this trivial insulator has none of those features. It's not compressible, it's incompressible because density is fixed as you change the chemical potential. It's not a superfluid, it's not gapless, it doesn't have any broken symmetry. Okay. All right, so now we can ask what's happening in between? How do we go between these 2 states? And given the very strong difference between the trivial insulator and the superfluid, there must be a phase transition. And that's what we want to describe today. Okay, all right. Any questions? All right, so we want to now do a little better than perturbation theory in W, because we really want to go to large W. And usually that's a very difficult task, but in this case, the main trick of condensed matter physics, which is the mean field theory, actually works pretty well and gives you a pretty good picture of what happens. So let's do a mean field theory. So the general idea of mean field theory is that it's really a variational calculation. And you're going to approximate the many-body wave function by some wave function you can handle. And the wave function we're going to use is a wave function that's a product wave function. It's a product of wave functions on different sites in the grand canonical ensemble. And that's the general feature of any mean field theory. and that it's a product wave function of some simple local Hamiltonian. That's what we're going to use. And then, actually, it's the first thing you should apply to any problem you're faced with. In this case, it works pretty well. And we'll see that eventually there's a few special regions where it doesn't work. And that's kind of what I want to get to by the end of this lecture. So let's just do mean field theory first. So, as I said, it's a variational calculation. So the way you do a variational calculation in quantum mechanics is you guess a wave function with some parameters and you optimize it. Well, that's a little hard to do for many body systems because wave functions are hard to write down. So what we do is something very similar. Rather than guessing a wave function, we guess a Hamiltonian. That Hamiltonian has some parameters, and we just say that the ground state of our guessed Hamiltonian is a variational wave function for the actual Hamiltonian. So we guess a Hamiltonian, which is called H mean field. And what we're going to do is we want to be near the Mott insulator. We want our theory to recognize the existence of Mott insulators. So we're not going to perturb the second term there. So it's going to have exactly the same second term. And of course, the troublesome property, the first term was easy to deal with. The troublesome property of the second term was it involved different sites. So what we're going to say, we're not going to involve different sites. We're just going to say this is equal to something I call psi B, BI dagger, minus psi B star. Where psi B, in fact, we have only one variational parameter. It's a complex number, and in fact, the phase of it won't matter. So this is our mean field Hamiltonian. Psi B is a variational parameter, and the nice thing about this Hamiltonian is that it's sum over site. So I can diagonalize separately on each site. It's still not exactly diagonalizable because there's an infinite number of states on each site. N can be 0, 1, 2, 3, 4, 5, and this will give you various matrix elements between all of those states. But it's easy to put on a computer, and you can just diagonalize this and get all its energy eigenvalues for any value of psi B. Okay, so having got that wave function, our trial wave function will be just product on I on psi, which is the ground state of mean field. All right, I. And each mean field times field. Well, here I just take H outside I and some energy E0, which will be a function of psi times psi mean field. Okay. Our task is simply to, well, actually not to determine E0. We don't minimize E0 because we're not interested in H mean field. We take this wave function and we minimize the full Hamiltonian. So what we have to do is minimize psi trial. Okay, so that's a description of the usual Hartree-Fock mean field. This type of approach has many, many names, variational calculation, anyway. So in principle, it's very simple. In practice, there's a bit of algebra involved for actually doing all this work, which is done on the board in the notes, and I certainly won't do it on the board. So basically, you have to figure out what's the optimum value of psi for this energy. All right, and you can also see now this psi is exactly the kind of thing I need to get a superfluid because it's creating bosons out of the vacuum, and each time it creates a boson, it has the same phase phi, and you can see that. So this will give you some state at fixed phase phi, and this wave function, if you stare at it hard enough, is essentially a form of the Boglie-Ball wave function at least when U is very small. It becomes exactly the Bogoliubov theory. The details of that one. We'll see how it maps onto the path integral version of the Bogoliubov theory pretty soon. All right, so this is what you have to do. So to figure out the best value of psi. Now that's hard to do in general, but so what we're going to do is something simpler. We're going to expand in power of psi, which turns out to be actually quite sufficient. So this trial I'm going to say is some function, some constant. Let's call it E, and then there'll be just some in the notes. Plus R times mod psi b squared plus b to the fourth u and so on. So what we do is we pick a psi b. Yes.
I can ask if psi b depends on I or not.
No, you can choose it to depend on I, but we'll choose not to. If you choose a psi b that depends on I, then you can get supersolid states, which will be states that are both superfluid and have some density amount relation. But for this simple model, it's pretty clear that doesn't happen.
Like my pocket's lit up.
Okay, so you can expand this in powers of psi, and you can see that because it, and since you're expanding here about psi b equals 0, so psi b equals 0 is just the mod insulating Hamiltonian, or the trivial insulator Hamiltonian that we had above there. So we can be pretty sure that as long as there's an energy gap here, that this expansion makes sense. That means that this expansion makes sense except at these points, the transition points. So as long as we're not at those points, this expansion will make sense. Okay, so now there's just an exercise to determine, which can be done analytically to determine the value of R. So R is known. It turns out to be, let me just write it out here. R turns out to be chi 0 times 1 minus W chi 0. Chi 0 is like this is charge susceptibility. It depends on this integer n, which is in pink over there, which I'll call n0, n0 plus 1 over u n0 minus mu. Okay. So there are two terms really here. And these corresponds to adding a particle, removing a particle. And this energy denominator is the energy gap to adding a particle and removing a particle. So it's just standard perturbation theory, just a little bit more complicated because you have two different Hamiltonians you keep track of. Anyway. All right, so you have this expression here, which depends on n0, which depends on mu over u. And the dependence on w is relatively straightforward. But the dependence on mu over u is quite singular because n0 depends on mu over u. All right. So now you have this expression and you can plot a curve, which is the curve r equals 0. So when r equals 0, that's the boundary between the state where you preferred not to have any condensate, which is the r greater than 0, and r less than 0, where you're going to get a condensate. Okay, so let's draw that curve over here.
Subir, is it possible for you to explain how you got these terms again? I think there's some confusion as to how the operators B dagger and B act on the psi mean field at every side.
Okay, let me say that again. So here's your Hamiltonian. Psi B is just a number. There's a Hamiltonian. And the states of this Hamiltonian, the Hilbert space you're working with, is just the states. You can just drop the I. The Hilbert states are just n, where n goes from 0, 1, 2, n is a positive non-negative integer. So for each site, you have these n boson states. And the action of the B on these states is the usual harmonic oscillator action. Sorry, n minus 1. And similarly with B dagger. So this is the action of B on these states. So you take this Hamiltonian and you find its ground state in perturbation theory. You do second order perturbation theory in psi B and psi B dagger. And you also find its wave function, the ground state wave function in perturbation theory in psi B. When you take that wave function and you evaluate this quantity, which is the original Hamiltonian. So that's a bit of work. I mean, I would spend the whole lecture going through it. There's a little bit more of details in the notes, but it's not much more than the kind of quantum mechanics you learn in the very first course. You just need to know harmonic oscillator matrix elements and first and second order perturbation theory.
Hello. Yeah, just 1 second. So the psi mean field at every site is n or 1 or 0. What is the actual?
So this state here.
Yes.
So this state is a linear combination. So psi mean field. Let's just drop the I label. It's the sum on I Ci of Ni of n. Sorry, sum on n Cn n. So you can have 0 bosons, 1 boson, 2 bosons, 3 bosons, and so on. And there's some coefficients here. And so you have to use perturbation theory to determine these coefficients.
Okay, thank you. Thanks, Subir.
Yes, I agree.
With that ontology for psi mean field, you didn't really need to introduce H mean field. You could have just said that your trial wave function was of this kind.
Sure, but then how do I write down the parameters for psi, H mean psi? Yeah, you could take the most general wave function, which is a linear combination of different states. Then all the Cn are a variational parameter. That's an even more general wave function. You could do that if you wish. But in fact, you can show once you make this, the optimal choice is in fact given by H mean field with just one parameter.
You'd expect that the least disfavored n is the one you need to include probably. There's a favorite value of n in them.
Yeah, and there's some corrections, but actually there's a further statement that even if you took the most general Cn and optimized all the Cn,
yes,
the energy you'll get will be equal to the energy you'll get by this wave function obtained with just one variation parameter. They coincide. You actually don't gain anything by doing that. Okay.
Hello.
Yes.
Hello. Yeah, so my question is that the mean field Hamiltonian that you have written, is it based on some guiding principle that the form that you have written should be like that, or could it be
the guiding principle is, yeah, we'll talk about that. It's one of factorization. So what we're really doing, and that's and in the future, this is what we're going to do. Every time we meet a term that we don't like B dagger I, bj, we just replace it by expectation value of B dagger I, bj plus B dagger I expectation, and then minus the two expectation values to make sure you don't double count. So there's this simple rule. I'm sorry, hopefully you can all see it. Whenever you have an operator that you want to factorize, well, you factorize one and then you factorize the other, and then you subtract the products of the two factors to make sure you don't double count. And this is the usual Hartree-Fock procedure applied to bosons here. And that's really what I'm doing. So, but this is kind of an uncontrolled, it seems like rather ad hoc. At least in this first treatment, I'm trying to make it much more rigorous in the sense that in the sense that the variational approximation is rigorous and gives you an upper bound of the ground state energy. If you do it this way, you have no idea what you're doing, but in fact, it's equivalent to this. Yes.
Thanks.
Should I be surprised that this method works, given that the state is factorized at all the sites, there's no entanglement and so on?
Well, no, I mean, this is a mean field theory. The question really is the actual state are the major properties of the actual state accessible in some kind of continuous way from the state that you obtain? Or is there something really different going on? And for that, yeah, we'll see that there are only special points where there's something a bit different. It's of course, if you want to really get the exact wave function, you have to build in 2-particle correlations, 3-particle correlations. So the statement is that that procedure is in some sense convergent. You start from this and you can converge it by adding a few more things.
The statement is that you get qualitative agreement, not that you get quantitative.
Correct. Yeah, you have to put in further short range entanglement. You don't have to put any long range entanglement. Yeah.
For small W, I think it's obvious that it's going to work.
Yeah.
It's surprising for large values of W.
Well, I mean, also for very large W, it's kind of clear because you just going back to BEC theory. But as any between, we'll find it trouble. Okay.
So,
yes.
Hello, sir. So are you considering it as a dividing it the system into clusters and then considering the clusters are equivalent?
You could say that, but it's not really a cluster, it's just a single site.
I mean, then you can.
I'm assuming translational symmetry. I'm assuming that I don't have a ground state which breaks translational symmetry. Which it could, but for this simple model, it doesn't. We know from numerical studies.
But does this fail qualitative linear phase transitions where you have some CFT type situation?
Yes, of course.
Then there is definitely a long range.
Yeah, so I'm coming to that, of course. That's the remaining part of this lecture. All right, so what I was going to do, thank you for all the great questions. I'm just going to plot in this phase diagram here, this locus of the curves r equals 0. Okay. Orange, maybe. So let me remove all this. So the curve looks something like this. So this keeps going forever. So this is the curve r equals 0. There's many branches of it, like this, and so on. So what we find are the famous lobes, usually called the Mott lobes, but let's call them the trivial lobes, where the density is quantized. So everywhere over here, the density is fixed to n equals 1. Everywhere here, this is the only state where we know the exact wave function, even for non-zero W. The exact wave function here is 1. There's nothing. There are no particles, and that is the exact wave function. Here, we don't know the exact wave function. You can determine the exact wave function in perturbation theory in W, or your preferred method. It is a complicated wave function, but we do know that the density is quantized. It doesn't change from exactly n equals 1. And that's because this perturbation operator commutes with the total number of particles. So if you start, we know that the ground state here has a fixed number of particles in any system, then adding that is not going to change the total number of particles. And then if you assume translational invariance, then the average density on each side must be equal, and so must be equal to exactly 1. And that's exactly 2 and exactly 3 and so on. And also, not surprisingly, the point where the gap vanished is where, at least in this theory, we're concluding that the system for infinitesimal W becomes a superfluid. That may well be the correct answer. It depends on all kinds of details that we are not able to answer right now. There could be, it could also depend on additional interactions, some, other non-on-site interactions. So the whole question here is really a question mark. And we're going to talk a lot about it. In particular, a big part of the next few weeks, we'll be talking about the density n equals 1/2. That's really the case of most importance. When the density is exactly half filled, what are the other possibilities? And there's a rich set of possibilities here, especially in 2 and higher dimensions. But we're not going to address that now. What we want to address is the nature of the phase transition along these lines. So can we describe the theory across this line. Everywhere else, we have a pretty good theory. Here, this is just the trivial insulators. This is the vacuum. And in here, at least for large W, we have the Boglie-Ball theory that we talked about last time. All right. So now the remaining question is to address what happens here across this boundary. And there turns out to be actually very subtle behavior and a very interesting richness in what happens across the orange boundary. But let me also draw what are called the isochords in the superfluid. So the superfluid, as I said, has fixed as variable density. But suppose you don't know your chemical potential in an experiment unless you know your density. So and you want to get some help from this phase diagram. Well, so then what you have to do is find the value of mu for every density. Well, if you're in the insulator, then there's a range of mu's over which that density is allowed. But in the superfluid, there's a one-to-one relationship between the chemical potential and the density. And that's also something you can work out. If you take this wave function here, the mean field wave function has some density. So you can just work out what the density is as a function of W over U and mu. And then what do you find? Well, so for example, you could take the density n equals 1. Okay, I don't know the exact curves, I'll just draw them schematically. There'll be some line here and it'll actually meet right at the tip. This is the isochord with density n equals 1. Then density a little less than 1, you'll find it goes here. Then say density a half, it will also go here. This is a half, something like this. Then this is close to 0, so on. So here the density varies smoothly. And then as you increase the value of U, you get these pinch points, at least in this mean field theory, where all the densities meet, except the integer values. The integer values will end at somewhere on the lobe. So there'll be special points here, and then this is a bifurcation point. If n is greater than 1, it's going to go there. And so on. And another bifurcation point with n equals 2. It's not necessarily a straight line, it can have some strange shape. And if you're varying the chemical potential here, you don't notice this at all. There's nothing special about n equals 1. You just go right through it, n equals 2. But the closer you get to this point, then you notice something special about n equals 1, and there's clearly some singular behavior going on here.
What about n equals 0?
Yeah, n equals 0 is special, it just keeps going forever. It doesn't turn around. It doesn't turn around because there are no hole-like excitations out of the vacuum. It's only particles. All right, so just from this picture, you can see that they turn out to be, well, 3 different types of phase transitions. There's one phase transition here, which is fixed density. So different types of QPT. And of course, I'm not going to talk about here. I'm just trying to stay at finite W. So there are 3 different types of QPT. One would be at fixed density, fixed integer density. If you fix your density at exactly some integer value, which is, the system often does that on its own in the co-random system. It's not something you have to really work that hard. You can just find some integer density. And then you vary the hopping or vary U, then you'll go on this line and meet the tip here. And so we want to understand what happens at the tip. And that turns out to be a relativistic field theory, or CFT. Then there's the increasing density transition. Sorry, let's call it another question of how you think of it. Yeah, let's call it increasing density. That is starting from a trivial insulator and from an insulator. And that will turn out to be the Bogdanov theory. There's also decreasing density. And that turns out to be the anti-Bogdanov theory, if you wish, of holes. Okay, so yeah, there's plenty of time. I think hopefully I can show these things before we're done today. All right, so what do I mean by the increasing density transition? Starting from an insulator. Well, the transition we actually talked about last time, without really specifying it very carefully, was a transition from the trivial vacuum to this vacuum, going this way. So I start from the empty state with the wave function at exactly 1. And then I had what I call the dilute Bose gas. What I was really doing was going across this phase boundary in the chemical potential picture. Now this transition at low energies is the Bogdanov theory, but it's also the Bogdanov theory at high energies, because in some sense the vacuum is totally trivial here. So as a result, there's certain renormalizations that you think would happen in general. They don't, because the theory is kind of trivial over here. So in this region, if I write down the Green's function of a boson, that's equal to omega minus Ek, where Ek is the dispersion of a particle, because if you have an empty state, the only thing you can do is add a particle. So that's an exact eigenstate, just one particle in the vacuum. So this wave function all the way up to this point has no renormalization. It's exactly that. So there's no mass renormalization, there's no wave function renormalization, there's nothing. And that answers some of the questions I think Nadia and Edward were raising last time about analogies to QCD. And it's different here because this vacuum state is trivial. However, there's another increasing density transition. This one, that's another increasing density. But this is type 2 here. This is type 1 here. And another one there. These are not as simple. There are some renormalization, but they're finite renormalizations. And you know, the concerns that you expressed last time will apply over here. But close enough to the critical point, the exponents and the nature of the transition, you know, apart from some unknown effective mass of the bosons, are you know, some wave function normalization, which are just finite numbers. The theory is essentially the Bogdanov theory. So you can also apply the Bogdanov theory in kind of a dense situation. And the way you think about this is also very simple. So suppose you're in the mod insulator. We have exactly one boson per site. And now you change the chemical potential. You change the chemical potential, and as you go across this transition, the density changes a little bit. So you just add one particle, say. And with the particles you add are dilute. So to leading order, I can just forget about these bosons here and just consider the extra boson. And that extra boson that's moving around, the only effect of these stationary bosons will be its hopping matrix elements will be larger by a factor of 2 because of this Bose enhancement factor, the square root of n that I wrote this factor here. But other than that, the fact that there is this insulator sitting around doesn't change anything. And this thing can just move around. And so the Bogdanov theory, the theory of dilute bosons, applies to this extra boson. And that's kind of how you understand this result. And this also shows you this Bose enhancement factor Also shows you why the lobes start to shrink. As you have more and more background bosons, this extra boson is moving faster and faster because it's got a higher, larger matrix of it. And so that makes it more likely to be a superfluid and condense. So the lobes start to shrink. Okay. And this theory 3 is exactly the particle-hole conjugate. There you're talking about, that doesn't appear here, but would appear here. And for theory 3, you have a density of holes. You remove a particle, and these are dilute, and they move around. And that gives you essentially the Bogoliubov theory, but for vacancies, not for particles, and so on. And what happens right here is, of course, you have to consider both particles and holes, and that's how the origin relativity. Okay. All right, so I've given you the main results. Now let me sketch how you can derive some of this. Any questions?
Transition 1 supposed to be like a Wilson-Fisher.
Yes, yes. All right, so at this point, we're going to kind of switch gears in our philosophy. We're not going to try to actually determine some numbers and do a strict variation calculations. We're just going to be interested in general features of long wavelength theories. And so we can be a little sloppy about various factors because we're not going to determine the factors with any accuracy anyway. But it'll tell us something about universality classes and natures of the long wavelength theory and all the results that I've just claimed. So the general trick here is a trick we're going to use a lot, which is the Hubbard autonomous transformation. So what we're going to do is take the path integral of that original Hamiltonian, so dB dagger. You take the corresponding Lagrangian anyway, full Lagrangian for H, which I think I wrote down at some point last time. And we're going to take the very first term, the hopping term, and decouple it by Hubbard's autonomous transformation. So one of the terms that we'll see here will be something like exponential minus integral 0 to beta d tau. Let me write it this way: sum on ij wij I ej, and there's a minus sign. Well, I just went to skip the step. Yeah, I think there is a minus sign here. Okay, plus emission conjugate. So we just take this term, which was the term we approximated in our main field theory. This particular term we treated exactly, and we're going to continue to do that. So we want a theory that knows about the mod insulator, and the only way it knows about it is if you keep this exact. Okay, so we're going to decouple this into a path integral, d psi, and this psi will turn out to be essentially the fluctuating version of the mean field parameter we had earlier, d psi b star of exponential of minus, okay, I can't promise to get all the signs right here. Or process sum on ij psi b of I, W inverse of ij psi b of j minus some psi b of I and tau, in fact, bi dagger plus emission factor. Okay. So this is the famous Hubbard transverse transformation. We just take some quadratic form, a product of two operators, and decouple it in terms of an auxiliary field psi to a term that's linear in the operators. So the quick way to check it is just to complete the square over here and complete the square and then shift psi. That gives you an overall constant we don't care about, and then you reproduce the left-hand side. So the tricky thing here is, which I am going to really put under the rug, is that this quadratic form has to be well defined. This matrix has to have positive eigenvalues for this thing to make sense, for this inverse to make sense, and for the integral to make sense. And if you do it carefully, you find that it does have positive eigenvalues near zero momentum at long wavelengths, but it doesn't at high momenta. There's a way to fix that, and I discussed that in my notes, but all right. But it's a way to do this completely rigorously, although when you do it sloppily, there seem to be some negative eigenvalues floating around. Okay. All right, so now what you notice is this is an exact transformation. What you notice if I just replace psi b by a constant, I have my own mean field Hamiltonian. Okay, so therefore, as far as the B integral is concerned, this integral is concerned, the B integral now involves only single sites. Okay, so if I just look at the B integrals,
Side B is complex.
yes.
So you have daggers there. So it's side dagger.
Oh, thank you.
Yeah. And then you complete the square.
Yeah.
So you subtract BB dagger and then you have to add BB dagger.
Correct. Correct. Yeah. So when you
the same sign that you have there, but is this the sign? This is the same sign you have on the left.
Well, so there's a W inverse over here, so you have to be a little much more careful than that.
Well, it doesn't matter.
Yeah.
Number. You get the same sign as on the left.
Yeah, I think it's correct. The signs are correct, provided W is positive. But more precisely, provided the eigenvalues of W are positive, this is well defined.
But that means that the action is minus W, B dagger B, for positive W.
Yes, that's correct. So I did put the minus sign there. Yeah, I think they got it right.
But then the action is not bounded from below.
Well, sorry, this is I mean, there are other terms in the action which are coming from, that's right, if you only have bosons at Hall, you can put all the bosons lowest energy state as infinite energy, so negative. So it is not bound from below. What bounds everything is the interaction terms. You need the interaction to bound action. This is just a number as far as I'm concerned. What I want is that this path integral over psi to be well defined. And that requires that this quadratic form have positive eigenvalues. But this is as if you just let B run, it's unbounded. That's just simply the statement that free bosons are unstable.
What I think is confusing is that your Hamiltonian is minus W times hopping.
Correct.
So, I thought the Hamiltonian, the allowed approximation to the d by the x squared.
That's right, it is.
Then the hopping term is negative.
Well, okay, so if you have the following Hamiltonian, minus W sum of various neighbors, B dagger I, Bj, that gives you dispersion, which is minus W cosine K, which looks like this, which is a minimum at K equals 0. And so that's K squared.
Thank you.
Okay, so now the advantage of this transformation, first of all, I'm making contact with the mean field theory, except my mean field parameter now become a fluctuating field. And second, as far as the integral over little b is concerned, that again splits into products on sites. So I just have to evaluate the integral over little b. And then I'll be left with a path integral over psi. That's complicated because it couples the different sites together. But we'll have to worry about that later. But for now, let's evaluate the integral over little b. So then I have the following integral to evaluate, which is going to be a function now, let me call it z a function of psi or psi b. I do this on every site, so there's no site label. It's dB dagger exponential of minus d tau d dagger dB d tau. And then I have the interaction term. That's u. Something a path integral that's minus u mod b squared plus u over 2 mod b to the 4th. And then I have that term minus psi b of tau b dagger minus psi b dagger of tau b. Okay. So this is what I have to evaluate. And it's actually a very similar thing to what we did before when we did the mean field theory. The only difference is that psi b is time dependent. If psi b was a constant, evaluation of this path integral is completely equivalent to just diagonalizing the mean field Hamiltonian. It's exactly the same thing. Just a single site Hamiltonian with some source term psi b dagger. So this is the thing that I have to now evaluate. And I have to allow psi b to be a function of time. Okay. So to do that, you have to do time-dependent perturbation theory. So this is basically equivalent to the time-ordered product, exponential minus psi b of dagger plus the well, also have the time dependence. You have the free time dependence of the mean field Hamiltonian, the psi star of tau b of tau, and I have to evaluate this time order product in the mean field Hamiltonian. That is, I take the mean field Hamiltonian I had earlier. Sorry, not the mean field, just the single site Hamiltonian. So this has to be evaluated in Hamiltonian minus mu n plus u over 2n times n minus 1. So here's a very simple Hamiltonian. We know all its eigenenergies. So therefore, you know the wave functions and the time evolution. You have to take that time evolution and evaluate this time order product. Okay. A bit tedious, but that's really all you're doing. Again, only involving tricks from undergraduate quantum mechanics. All right, so this I'm going to write. So you do that. So this I'm going to write exponential some d tau of some Lagrangian psi of tau.
Subir, could you move the board up a little bit? I don't think we can see it.
Sorry. Yeah. Okay, so just to summarize, I did the Hubbard to Transverse decoupling. I reduced everything to a single path integral on a given site of a Hamiltonian, which is just the Hamiltonian, the relevant mod insulator, starting from here or here or here. And then I just have to evaluate this time order product. Okay. So when you do that, you're going to get some expansion. And so you pull all this together, okay? You also take, let me call this L0 of psi. You have an additional term.
I have an elementary question. Why
Yes.
do you need the time-ordered product?
Huh? Sorry?
Why do you need the time-ordered product?
Because this psi b is a function of time, the unknown function of time.
But everything here is classical, so the ordering doesn't matter.
No.
No? You're doing
So I'm doing this path integral exactly.
yes.
So now the reason I can't do this path integral exactly is because of this interaction term.
Yeah.
But however, I can still do it. At least formally, I can map this to this because that exact path integral over B is the same as the time evolution under this Hamiltonian. It's not a free boson Hamiltonian. And so basically, I'm just evaluating the time expectation value of this in this Hamiltonian. So this is not Wick's theorem. This is way beyond Wick's theorem. U is being kept exactly. I don't have any Wick's theorem here, but I'm just evaluating this. I can't usually evaluate it, but the way I evaluate it is by expanding in powers of psi. And the reason I'm happy to expand in powers of psi is because I'm crossing a phase boundary where psi goes to 0. The psi is 0 in mean field theory on these orange lines. So near the boundaries, I can expand this in powers of psi. So if you wish, I can just expand this out in powers of psi. And then I have to do the path integral for B exactly. But I can do that path integral exactly because I know all the energy eigenstates of this Lagrangian. Okay, so when the dust settles, I'm sorry my boards are so messy, but the notes are not as messy. All of this is in the notes. So when the dust settles, what do you find? So first, let's look at what happens for constant psi. So I want the full Lagrangian L of psi. There'll be a contribution from here. And I'm sorry, there'll be a contribution from a term that I just erased, the Hubbard-Sachdev term with the W inverse in it. So I'm going to get L of psi. So I'm going to expand in powers of psi. I'm also going to expand in derivatives of psi, time derivatives. Psi only depends on, at least in this part here, on time. The Hubbard-Sachdev term does have a term that depends on space. So I'm going to expand in both space and time derivatives of psi. But let's look at the constant terms first. Okay, so the constant terms turn out to be, so R tilde psi b squared plus some u. This is a different u. We got u tilde over 2 psi b to the 4th. Where this R tilde, my glasses now, it's important to get this right. This R tilde very closely related to the R I had before. Well, turns out to be, so A is the lattice spacing, turns out to be 1 over ZW. So this comes from the inverse of the W in the Hubbard-Sachdev transformation. And this is just high 0 that I had before. So in fact, the equation, everything has been done so that the equation this equal to 0 are exactly the orange lines here again. So this mass term in this condensate vanishes on those orange lines. Okay. And there's some U, and then there will also be some gradient terms which are well defined. Spatial gradient that comes from the Hubbard-Sachdev terms, which I won't need. Well, grad psi b squared. I call that K3. Okay, so all of this you could have just guessed without too much work. It has to be of this form by Landau theory arguments. But there's something more beyond Landau theory that we have to put in, related, of course, to the very singular shape of the phase boundary, and also in the time derivative terms. Well, you can kind of guess the form of the time derivative terms. There will be some coefficient I call psi 1, psi b star, d psi b, d tau, plus k2, d psi b squared, so on. Okay, so now really the question is, what are these K1 and K2? Yeah.
Where did the spatial derivatives come from?
Yeah, that's from the term I erased. Let me write it out again. So there was a term like this, d psi exponential minus someone ij, wij inverse, psi b of I, psi b of j. So this is a matrix which is non-zero on the nearest neighbor lattice matrix element. So when I expand this out, this Wij inverse is basically 1 over minus 2W cosine k, something like that, with some constants. I don't know, something like that. So you when you expand this out, you will get the spatial limit.
So this did not come from doing the integral, just from copying what.
Just taking the long wavelength limit of this.
Without the integral over psi.
Oh yeah, no, I haven't done the integral over psi.
The integral that you wrote, this is not included.
Oh, excuse me, thank you. Yes, it's not. It's not. Yeah, it came from this term. All right, so here's my Lagrangian, and the problem, I've reduced everything now to evaluating the original Hamiltonian. I've evaluated Z of psi b, and that's equal to exponentials of this. No. Yeah. Z of psi b is the exponential integral of this. Okay, so that's Z over there. Exponential minus integral over space, integral over time of L of psi b.
Hello.
Not that Z, I'm sorry. I will just erase this. Look to my notes for the precise notation. The original theory of the original Hamiltonian trace e to the minus beta h, but these series of transformations that have been reduced to integral of L. Okay. Question?
Yeah, so is there any other term corresponding to psi star, psi b, del psi b, del tau? I mean, other term means Hermitian conjugate of that. No, the K1.
Yeah, there's an absolute value here. This is an absolute value.
No, K1. Term corresponding to K1.
You want to put the time derivative on psi b? Psi b star?
Yes.
You can just integrate by parts. And
okay. Yes.
Oh, okay. So this term is purely imaginary. Okay.
Mm-hmm.
All right. So now really the whole. Yes, go ahead.
How do you get L psi from this time order product? Are you guessing this?
No. I mean, if you just work hard enough, you can get all of these coupling constants from evaluating this time order product. So here's the thing you have to evaluate. You have to do two things. You evaluate this thing for this Hamiltonian. This is a non-trivial Hamiltonian because it's not free bosons. So it's exactly what you do in time-ordered perturbation theory and Wick's theorem, except your Hamiltonian is not a free particle Hamiltonian. It's an Hamiltonian with interactions. So you're pretty much forced to expand in powers of psi. You can't do it analytically. So you expand that in powers of psi. And you also take the Hubbard-Tutanovich term, the W inverse term, and you expand that in gradients of psi. And so the W inverse term will give you this, and also a constant. It'll also contribute to this. And then this time order product will also contribute to this. So if you notice here, this is coming from the W inverse term. This chi naught, you can almost see it right here. Chi naught is just the two boson correlation function. So you can just see that chi naught is minus the time order product of B of tau, B dagger of 0, integral over time in the Hamiltonian, this Hamiltonian. Okay, because you know all the eigenstates of this Hamiltonian, you can evaluate this exactly by the usual spectral representation. So if you do that, you will get the chi naught, which I wrote down on the board a few boards ago. It's in the notes, so I don't want to mess it up. But you remember the chi naught, you'll get exactly this chi naught. It's just the two boson Green's function in this trivial insulator Hamiltonian. Okay.
Sorry, and how about the time derivatives? Are we guaranteed that they're always small, the time derivatives?
No, no. So this will be, the assumption is that there's a second order phase transition, and near the second order phase transition, I can do a long wavelength theory. Except one caveat, along this line, because this is the trivial case, because n is 0. So these boson correlation functions are essentially exactly evaluable. And along this line, in fact, you're not making no expansion. Along that line, the first line, you get exactly the theory we had last time. K2 is exactly 0. K3 is just given by Bayer dispersion. U is just the actual U of the Hubbard model, and R is just the chemical potential. So at least at 0 temperature, this theory is kind of trivial and is exactly the Vogel-Bell theory we talked about last time along this line. But along the other line, it's complicated. We don't know exactly what it is. Yes?
To do this at 0 temperature instead of the trace, you just take the expectation value in the ground state of the simple Hamiltonian?
Yes, yes. I've done all the calculations, in fact, at 0 temperature.
Well,
yeah.
I noticed that they made more sense then.
Yeah, okay, sorry. Right. I mean, there's probably many other ways to say this. Just working in imaginary time, and then, but betas at various places is sent to infinity. The expressions are given for beta equals infinity. Yes.
So one question here, you have integrated out all the B and B Dagger fields, and
right.
Then you, then you got that Lagrangian, but
yes.
Then what is the chemical potential where you are doing this calculation?
You pick a chemical potential, it could be anywhere, and everything here depends on the chemical potential. R tilde depends on the chemical potential. You already see that because chi naught depends on the chemical potential.
Yes.
We write down what chi naught is. That's really the important quantity here. Chi naught, we wrote it earlier, is N0 plus 1 over U N0 minus mu plus N0 over mu minus U N0 minus 1. So remind you, so this is really essentially the two boson correlation function. You can add a particle, and then this is the gap to adding a particle, or you can remove a particle, and this is the gap to removing a particle. And here there's an explicit dependence on mu, but there's also a dependence on the integer N0 on mu, as in this picture. N0 is 0 here, and 1 there, and so on. All right.
Hi.
Yes.
Can you repeat that part of infinite temperature? Like you are doing a finite temperature calculation, right?
Right. So this is the expression for chi0 at 0 temperature.
Oh, okay.
If you just evaluate this, yeah. You can think of it as essentially second order perturbation theory of the ground state energy of the Hamiltonian to add this term. So suppose I give you this Hamiltonian, where the top term is just the Hamiltonian right here. I just add psi b b dagger plus psi b dagger b. I do second order perturbation theory in psi b to find the correction to the ground state energy. And the correction will be chi naught times psi squared, or minus chi naught times psi squared. So it is really nothing but second order perturbation theory. Or you can evaluate this, that's the tedious way to do it. But the reason I'm doing it this way is because I want to get these time derivative terms. So that's a little bit trickier to do it, but by usual good old-fashioned perturbation theory. Then you have to do some kind of time-dependent perturbation theory. And since I'm working imaginary time, you might as well just take the time order product and expand it out. Okay, so now really the question is, what are these things? So what I've already told you is that along this line, K2 is 0. In fact, and the constants are trivial, and that was the theory of last lecture. Exactly. So the other thing we can see now is all depends upon what happens to K1 and K2. So if K1 is non-zero, then in the usual RG sense, since this has more time derivative than this, we can forget about K2. So as long as K1 is non-zero, you don't need to worry about K2. And we're pretty much back with the Bogoliubov theory. This is exactly the same path that I had last time, except the signs of, the coupling constants have changed. So when K1 is non-zero and positive, then you get the phase transitions of type 2, where you condense bosons above a Mott insulator, either above the trivial insulator with the empty vacuum or the trivial insulator with, I shouldn't have said Mott, with n equals 1 or n equals 2 and so on. However, when K1 is negative, then you will get the same theory, except this has an opposite sign. And that's simply telling you they're dealing with holes rather than particles. And that will be the phase transition of type 3. So the phase transition of type 1 at the Mott lobe, which is we identified as the fixed density transition, is also the point where K1 equals 0. So there's something very special about the point K1 equals 0. And so we really need to know what K1 is and see how it changes sign when it goes to 0. And it seems to be crucially controlling exactly where you have a relativistic field theory with non-trivial interactions and a non-trivial phase transition, which is the Wilson-Fisher theory. For those of you who don't know what that is, but we'll talk about that later. But anyway, if you ignore this, the theory looks relativistic because you have second order space and time derivatives. So really the question is, what is K1? All right. So now there's a very beautiful identity. You can work out what K1 is, theory and calculation. And K1 is equal to minus dr tilde dV. So here's our tilde that I computed for you. And remember the line of the phase boundary was r tilde equals 0. Okay. And the derivative of the line in the vertical axis, mu is the vertical axis here, gives you the value of K1. So where does it vanish? Well, it vanishes when the orange line is vertical. That's exactly the tips of the lobes. And so that's where you have the phase transition of type 1, which is relativistic, not in the Bogoliubov theory, only at that point, strictly speaking. Of course, not strictly at that point. There's also some singularities here, non-trivial exponents. So there's a whole window around here where you really have long-range entanglement, lots of non-trivial things to worry about, which we won't worry about today clearly. But it's already clear that's the point where things become relativistic. And that's also the point where the density does not change. Okay. So all these statements, well, you can first just evaluate K1 the tedious way. And you can find they're true. But ultimately, where does this come from? Okay, so the way you can derive this is by an argument which is rather similar to what field theory is called a 't Hooft anomaly. You take the system you have as a global symmetry. Let's go back to the original Hamiltonian. The details again are in the notes. Let me just sketch the argument. Here, hopefully I can get it right. So let me just take the original theory, the Z, which has both D and D psi. Let me be very schematic and only write down the terms that I need. There will be something like d dagger dv d tau minus mu d dagger b. The chemical potential couples to the density. And you have various terms. And then you have d psi b star and d dagger psi. Okay. All right, so this particular action has a symmetry. It's a global symmetry, which is B goes to B times e to the I phi, and psi goes to psi times e to the n5. Okay. That's just conservation of number of particles. But what if I make this a function of time? Well, that's not a symmetry. But so that's the typical thing you do in a TIFR anomaly calculation. You take a global symmetry and you gauge it. So you make it time dependent. That's not a symmetry, but it's almost a symmetry. And the reason it's almost a symmetry is that the only term that has trouble with this is this term. There's no other time derivatives on Hamiltonian anywhere. You put any interactions you want. There's only one term, this Berry phase term, which doesn't like this transformation. But you can fix that by just thinking of the theory more generally, where the chemical potential also becomes a function of time. So take a more general theory where mu transforms. It's just mu is an external parameter, some background field. You make it time dependent. And so if the sign's right, so there's a transformation of mu. If I make this transformation, allow mu to be time dependent, then I do have invariance of the partition function. All right, so I took this theory and I did a lot of manipulations of this theory.
Did you write an I in that one?
So,
yes, I did. Yeah, so it's becoming imaginary. Yeah.
Yes.
Yes. Yeah, so I'm just thinking of some, I'm now a mathematician. I have some path integral I have to evaluate. And I think of mu as some arbitrary complex number, which even depends on time. And I just noticed that this path integral has a certain symmetry for those values of mu. Now, the point is that all the manipulations that I did so far go through even for a time-dependent chemical potential, provided it's weakly time-dependent. And so the Lagrangian that I wrote down over there, at least, modular terms involve time derivatives of mu, which don't affect in this order. That should also be invariant under this transformation. And for that Lagrangian over there, I can forget about B. I only have to look at this invariance and only look at it to second order. So if I perform this transformation on this Lagrangian up here, and I assume psi is small, so I'm going to go to second order, then under this transformation, this thing is not invariant. This has a change about its size. So this thing will have a shift, which will be k psi b squared d phi d tau. So I want to look at other terms of order psi b squared. Well, the only other term that's about a psi b squared is here, which also depends on mu. And so r twiddle, which is a function of mu, will go to r twiddle function of mu minus dr twiddle by mu d phi d tau. Because mu just has a small shift, d phi d tau. So now these must cancel, and hence you get this relation. Okay. Oh, yes.
What is the Duft anomaly?
You're taking a global symmetry and you've gauged it, and you're looking at the effect of that. That's okay. There's an anomaly here in the sense that, what is the anomaly? The anomaly is the fact that when you do this gauge transformation, you pick up a constant factor having to do with the integer. Here you get e to the in phi, and you get I to the 2 in phi. There's a background term from the background density. So the value of the anomaly is the background density of the Mott insulator, and that has to be preserved on the different Mott insulators. So the fact that there is this integer number of charges here, you have to keep track of that, and that's the anomaly. The fact that, and that has to remain invariant, and that's why you have this relationship. Okay, forget anomaly. This argument stand on its own. I don't have to refer to anomaly. You don't like it, fine. This is the argument. I just do a time-dependent gauge transformation, and then I just demand that for a slowly varying gauge transformation for small psi b, it's preserved, and you immediately get this relation.
question.
Okay, great. I'm over time, so sorry about that, but that's pretty much where I wanted to get.
Hello.
Any questions?
Yes, sir.
Yes, please go ahead.
Sir, you got this relation K1 equal to minus del R tilde by del mu using the argument of global symmetry. But can we derive this relation using the way that helps us to identify this R tilde, U tilde, and so on? Just you construct the Lagrangian.
You can actually do, I urge you to do the calculation. So I spelled out a procedure where you can compute K1 from the microscopics. Just do everything I said. I laid out all the steps, do the time order perturbation theory, and you get K1. You can evaluate it. And once in my life, I've done it. And you'll get some number. You already gave it the expression for R tilde right here. And then you check that this indeed works.
Okay.
Yeah. Yeah.
That means there is a way.
Yes.
Hello.
Yes, go ahead. In India.
Yeah. So this R's tilde is a complicated function of mu, right? And
yes. It's a highly singular function of mu. But at least within a model lobe, it's very simple. They're just these two terms.
Yeah. So
once you go from one,
holds exactly or in some approximation. Like when you demand that this Lagrangians should be conserved, should not violate the symmetry.
Yeah, that's a good question. I mean, at this point, I've just presented it in terms of power series expansion in psi b. Now you can ask where this is an exact relationship in the way I've defined it. Now you can ask, if I take the actual position of the phase boundary, is the derivative of that actual position equal to K1? Well, that's also not a very well-defined question because even the value of K1 is not well-defined because of various normalizations that happen at the endpoint. So that becomes very subtle. But there certainly is a way, not in this way, but there are constraints that go in the eventual theory for the critical point that respect this symmetry. And there are various constraints in what identities you can derive on the full theory from this.
Yep. Symmetry should not be violated.
Or you can even make them slightly time dependent. Yeah, Edward.
In the region where K1 is non-zero, as we vary R tilde through zero, are we getting a non-trivial phase transition?
Yes, it depends on what you mean by a non-trivial phase transition. It's an exactly solvable theory. It's just free bosons near the critical point. It's essentially the Bogoliubov theory.
Sorry, that's what I was questioning.
Yeah, so. Yes. So you can think of the Bogoliubov theory as the theory of a quantum phase transition. And it's the theory of this quantum phase transition.
I had interpreted it as the theory inside the superfluid phase, not the theory actually.
Yes, but a better way to think about it, I would claim, is the following way. So let's imagine you're going here.
Yes.
So in fact, there's some critical point here in the grand canonical ensemble. So here you have, it's some mu c, which will be 0 for the Bogoliubov theory. Over here, the ground state is just the empty state, or the vacuum. Let me say it's trivial because it would even be any of the. And here the ground state is a superfluid. Okay. And so, for example, if you plot the density of particles, I'm going to plot the density on this axis, then the density of particles in the ground state, T equals 0, that goes smoothly to 0 at this point. And here it's empty, and then the density turns on. And so this is like a phase transition, where in the grand canonical ensemble, where you're breaking the symmetry here, not here. But it has dynamic exponent z equals 2. It's this theory that just that theory would put K2 equals 0. Now it seems like a trivial theory, but it's not entirely trivial because there's non-trivial renormalizations to two body operators. So in this theory, the Green's function, is just G0 to all orders. But if I take two-particle Green's function, then there's the interaction. And this can have non-trivial renormalization. In fact, in one dimension, it has a highly non-trivial set of exponents associated with it. So that's at this point. If you turn on finite temperature, then of course the density, so at finite, and this shouldn't be drawn on the same graph. I don't remember the iso cores here. But right here at finite temperature, you have a dilute classical gas. So the way you can think about it, there's some dispersion and your chemical potential is here. And at finite temperature, expanding a few set of very dilute set of classical bosons over here. And on this side, your chemical potential is somewhere here. And this is really the DEC of the boson, the condensate.
So, sir, one question is here you have shown that your chemical potential is imaginary.
Yeah, okay, let me just finish my statement before I come to, and as you go along here, well, no. So this is just a simple fluid state and this is the equals to, so that's along here. You can ask what happens along this line, then it's like a critical endpoint to a line of critical points. Is Z equals 2 on this line and Z equals 1 on that point. Sorry, question?
So the question was that you showed that the chemical potential is become imaginary for finite t.
That was only temporarily one. I was trying to derive a Ward identity. And since I was working in imaginary time, I had to make things imaginary. But and it's a lot easier to do it that way. But once I derived the identity, I made it back to real. But if you want to do everything in real time and then derive the Ward identity, then you won't need to make it imaginary. That's much more fun. I just live in imaginary time, sorry. It's easier to think that way.
Sorry, yeah. It's the question, but in the superfluid part, right? Is there a thermodynamic interpretation for R tilde? Or is it like the pressure?
In the what part?
In the superfluid side of
yes, here.
Is there a thermodynamic interpretation for R tilde? Like what is it, the pressure or something of the superfluid?
Well, if you're really doing this condition, it is just the chemical potential. R tilde equals that. Yeah. But here, no, it's just some tuning parameter. It has no simple direct relation to mu. This is some complicated curve whose position I can only get approximately. Okay, so we've gone way over time, but anyway, so you can see this incredible richness even in the boson Hubbard model. The summary then, really you should think of the Bogoliubov theory as a theory of a quantum phase transition from any trivial insulator to a superfluid, where you vary the density, just adding particles on top of some trivial insulator. And then there's another phase transition where you're not adding particles, but you're creating equal numbers of particles and holes when you're doing, and those can have very strong interactions that lead to a very different sort of critical point. And this is the only point in this whole phase diagram, at least in 2 dimensions, that has what we call non-trivial long-range entanglement. Okay, thanks.